Welcome to week 6 of Advanced Object-Oriented Programming. This is probably going to be the last lecture type video we're going to have. Okay, now in week 7, you're going to concentrate on getting your project together in presentation mode. So let's go ahead and get started. Okay, today we're going to be talking about concurrency, thread safety, and scalable design. Just kind of recap what we've done. We've talked about type-safe abstraction, scalable collection-based systems, robust exception hierarchies, and pattern-driven architectures, which was out of week 5. Here today, we're going to talk about the main thing is concurrency. Running things concurrent versus running things in parallel. Obviously, this goes hand in hand with or opposite of single-threaded, but we'll talk about single-threaded versus concurrent versus parallel. Okay, concurrency. Because everything works in a single-threaded mode, if you just attempted to do many or some of these items and run them concurrent or parallel, you're going to run into problems. Okay, so we're going to be talking about what do we need to adjust from a concurrency perspective, when all we've been doing is running in single-threaded mode. Okay, so today what we're going to be covering is Java's concurrency model, the thread lifecycle and scheduling, thread creation approaches, synchronization and race conditions, thread safe design strategies, concurrency hazards, asynchronous execution versus synchronous execution, and trade-off reasoning. This week is about correctness under pressure. Okay, so part 1, what is the Java concurrency model? Okay, Java uses a shared memory concurrency model. This means that there are multiple threads that share heap memory, and multiple threads means I'm doing multiple tasks or multiple things, and each thing is taking a thread. Okay, so that is what the general concurrency model is based on. Threads have separate stacks. Okay, as far as memory is concerned, each particular thread has its own memory stack. Objects are accessible to multiple threads unless restricted. So when I create an object, I have something in thread 1. It can use the object, and also in thread 35. Okay, it can use the object. Each thread has its own stack memory, which stores the method calls, the local variables. This means that when multiple threads run, the local variables do not interfere with each other. Now, a thread has a given life cycle. What are the steps? What does it go through? And here is the listing of the thread life cycle steps that basically exist. A thread becomes new, then it becomes runnable, not yet running, but runnable. Then it transfers into running. And once it's running, it can either be blocked or it can go into wait mode. Or if none of that happens, it will run until it's terminated. Okay, important. Java does not guarantee scheduling orders. So even though if I have multiple threads and I schedule one to start at 1 o'clock and one to start at 1:05, and something happened, there's no guarantee that the one that started at 1 o'clock is going to finish before the one that started at 1:05. Okay, so the guaranteed scheduling order is not guaranteed. Threads are managed by Java Virtual Machine and operating system and the operating system scheduler. Concurrent versus parallel. Okay. Concurrent says I'm running tasks that overlap. Okay, over time. I'll run task 1, then I'll run task 1A, and then I'll run task 1B, and then I'll go back to 2A. So tasks overlap in time. Tasks may share a single CPU via content switching. Content switching says that here that I start running one thread, I will basically swap those out to run something in another thread. And when I swap those out, separate memory will be used. Versus parallel. Parallel syntax execution simultaneously on multiple cores. So basically, just and to keep things simple, say I had five core memories, okay, that I'm executing. Okay, I can run in parallel, okay, five threads or five activities. I can run that in parallel. Uh, Running concurrent, okay, I can, if I only had one core, okay, I'm running concurrent. Okay, I'm single threaded at some point. So I'll single thread some work. I'll work on it, then I'll stop and I'll bring in another thread and I'll single thread it and I'll stop and I'll go and do a third thread. So it's really kind of sequential processing, but what it's doing is swapping in and out on those concurrent. That happens when I have one core. If I have multiple cores, I can actually do parallelism. So if we think about it, concurrency is about structure. You know, how am I going to structure the task and the threads? Parallelism is about hardware. How many cores do I have? The number of cores is going to kind of drive what it is that I'm going to be able to do at any one time. Okay, creating and managing threads. There's two primary approaches. I can extend the general thread class. So here I can say my thread extends thread, and I'm going to run it. Okay, in this particular case, all I'm doing here is putting a system out to the print line that says, okay, I'm running. But, you know, in reality, we're going to be doing a whole lot of other stuff during here. Or the other way I can do it, I can implement runnable. And this is preferred. Here I'm creating a class that implements the class runnable. Okay. From that, here, same thing. When I hit run, I'm going to say task is running. Okay. So it's better to do it this way, okay, than to extend the thread. And then we start the thread. Okay, so here, thread, I'm creating a new thread for my task, and I'm starting it. Why is runnable preferred? Okay, separate stack from thread. Separates the task we're doing from the thread. Supports composition, you know, as far as interfaces, and it's more flexible. Okay, so we have task-based approaches. Modern Java favors executive service and thread pools. Aha, what is this? Look it up. Okay, this is one of those cases I want you to do a little work. Again, this just falls a line. I would expect these aren't the only two things that you're going to run into that you're going to wonder what it is. Okay, you know exactly what is thread reuse. Okay. Okay, so here's the modern Java favors executive service, thread pools. Advantages are the thread reuse, controlled resource management, better scalability. Raw threads. Raw threads are something that we want to kind of stay away from. They're expensive, hard to manage, poor life cycle, bad things. Professional systems rarely use raw threads directly. And just thought this one was important to go ahead and lay it out to you. That raw thread refers to creating and managing threads directly using low-level thread APIs, such as the thread class, instead of using higher-level frameworks for your task-based systems. Okay. So that is what we want to stay away from. Okay. We don't want to get down to that lower level to manage threads. But here's an example where I'm creating a new thread, okay, new thread class. So here, when I started, I'm put out a system measure says I'm running, and then I'm going to start it. And I have started a thread. I can do this multiple times, creating multiple threads. As I said, whether we're doing it in parallel or concurrent. Okay, so that's the raw threads we want to stay away from. Race conditions, visibility, and atomicity. Okay, what this is doing is let's examine it. So this is the counter. Now, if you look at a counter, it's not atomic, means that there's more than one thing going on, or more than one step that we have to do in order to execute uh, this particular counter. Yeah. So this involves reading, incrementing what's there, and then writing it. And then the next time around, we're going to read it, we're going to increment, we're going to write it. Okay, that's what's involved in the counter. Okay, two threads can interleave. Okay? I can have one thread that's reading, incrementing, and writing, and I can have another thread that's reading, incrementing, and writing. Okay, at the same time. What that presents is the problem is you can have lost updates. You can read it, increment it by one, but before you write it, thread two also increments it. So what you thought was, I read it, it was one, I incremented, I got one, I wrote it, I came back, I incremented it by two, but before I could write it, I had another thread that incremented it to three. Okay. So in this particular case, two threads can be interactive, but I can lose updates because I'm having threads having capability to update the same variables. Visibility problem, one thread modifies the variable, the other thread can't see the change. Solution is to synchronize volatile or use atomic classes. Synchronize, here is where we're basically blocking out that once we get access to the counter, we basically have access, exclusive control to the counter until we release it. Okay, and that's where we're synchronizing access to that particular counter, is we're basically blocking it. Okay, designing thread safe systems. Let's see, I'll go back here real quick. Okay, you need to look up volatile and atomic classes. Okay. Okay, designing thread safe systems. Thread safety is not about sprinkling synchronize around everywhere, blocking everything out. It's about architecture. The concept of immutability. That's saying that, immutable objects are inherent thread safe. Once I set it, it's done. I can't change it, so there's no mutation, meaning there's no race condition. Encapsulation, okay, we're going to keep mutable state private. Yeah, I'm going to have it to where I do have variables that are updatable, but I'm going to make it private, which means that those particular variables only exist in the life of that particular class or that particular object. Okay, and they're internal within that particular object. So that's the encapsulation using mutable state fields, okay, changeable fields. Thread confinement, some objects should never be shared. Okay. Local variables should never be shared. Requested scoped objects should never be shared. Shared objects require synchronization. Thread confined objects do not. Thread confined says, I'm basically capturing and using everything I'm going to need in the confines of the thread, and nothing can be used that's outside the confines of that thread. Yeah, that's thread confined objects. Okay, design principle, reduce shared mutable state. This reduces concurrent bugs. Behavior patterns. Okay, we talked about these. We talked about the strategy, the observer, the command, and the state. Okay, and basically what we're doing here is just saying, well, what is the effect of patterns on concurrency? So, looking at the strategy, swap algorithms without shared conditionals reduces contention points. Observer, event-driven design decouples components, avoids type coupling within threads. Command behavior encapsulates risk, works well with the executor service, which I'm sure you went quickly to look it up when I mentioned it back in the first part of the first part of the recording of the video. Okay, State behavior patterns, is encapsulation, transitions, avoid scattered conditionals. Behavior patterns reduce shared logic. Okay. Less shared logic means less issues, less race conditions. Okay, concurrency hazards. Okay, the three primary thing is I can have race condition problems where I have unsynchronized shared mutable or shared changeable fields. I could run into deadlocks where I have two threads. Thread holds lock on one, waits for the lock on two. Thread B holds the lock on two, is waiting for the lock on one. These are both active at the same time. We have a serious deadlock that needs to be resolved. System freezes. Starvation, thread never gets CPU time due to priority imbalance. I always say thread one has priority and thread one never finishes. So it's basically locking out all the other threads from being executed. So never gets CPU. Professional engineers analyze lock ordering carefully. Always acquire locks in a consistent order. It helps that deadlock situation. Okay, asynchronous programming concepts. In synchronous, you call blocks until the result returns. Synchronous says, okay, I need, get me an apple. I'm going to sit here until you give me an apple. I get the apple, then I continue on to the next step. Asynchronous says, hey, give me an apple, but I'll come check later whether you actually gave it to me or not. And so I'm going to go ahead and continue and do something else while you're getting that apple for me. So that's basically what we're saying here. Asynchronous, synchronous blocks until the result returns. Asynchronous calls initial task. Results are handled later. We'll put the results somewhere and come back and process it later. Non-blocking systems improves responsiveness, increase throughput, reduces CPU time. All of that falls into the asynchronous advantages. Conceptually, synchronous waits, asynchronous continues to handle later. Modern systems increase asynchronous design. Not to have to sit there and wait for the answer, but while we're waiting, we can go ahead and do something else. Evaluating concurrency trade-offs. Concurrency adds performance and scalability, but it also adds complexity, debugging difficulty, and hard to reproduce bugs when I'm running things concurrency, and you think that makes sense. If I'm running 2 or 3 items at the same time and I have a problem, how do I duplicate that? So it's running in the same environment, the same sequence as I did before. Very difficult. Hard to reduce bugs. You must balance correctness, performance, and maintainability. Concurrency should not be added because it might be faster. It should be justified by workload. That is what should drive concurrency. If I have a heavy workload, I might want to use concurrency. If I don't have a high workload, you don't need to put concurrency in there just for the fun of it. Architecture reasoning. Ask yourself, does this system, this is what you should ask, have heavy computation, blocked I/O, serves many users, or requires responsiveness? If yes, that would be the key to say, okay, I need to put concurrency in these threads. If not, then simple threaded design could be superior and more effective. Simplicity is powerful. Always keep that in mind. So looking at the course introduction reflection, everything we've learned, generics, collections, exceptions, patterns, concurrency, where concurrency forces all these concepts to work together that we just talked about here. So in closing, the last week 6 in talking about the last lecture, formal lecture, today we learned to explain Java's concurrency model. We learned to create and manage threads, apply synchronization correctly, design thread-safe systems, use behavioral patterns to reduce contention, and recognize race conditions and deadlocks. What happens under asynchronous design as well as what happens under synchronous design, and evaluate concurrency trade-offs. Concurrency is not magic. It is disciplined engineering. Well, I enjoyed it, folks. We'll basically see you again when we go through the presentations. And I want to say I enjoyed having this particular class all through these first 6 weeks and into the 7th week when we start working on our projects. Everyone have a good one. Bye.